And welcome to class, guys. We're talking about section 6.5. This is probably the most important section out of all of chapter 6, and it's the main reason why we're interested in logarithms. So the three properties that we'll talk about today, if you see logarithms again, will certainly come up in some detail. And we're starting to get to applications of logarithms as well, right? So we're going to start to see maybe why logarithms are interesting in terms of the types of problems you can solve with them. Before I get into the objectives and sort of saying exactly what the properties are, there are three of them. Let me stop last time. So last time we were looking at two numbers. Let's say the log base b of capital N. And we said, okay, we're just going to plug that into our calculator. We get out some number x. And then we said, okay, let's also compute the log base b of m. And when we plug that into our calculator, we get an output of a y this time. And we were able to translate this into a little more information. So the first thing that we should recognize is sort of how to go back and forth between logarithms and exponentials. Here, it just means the power of x, right? So this first one up here is b to the power of x is actually the same thing as n. And the second equation tells us that b to the y is equal to capital N. And again, these two sets of equations are just the same thing, one in logarithmic form, one in exponential form. And as a reminder, the logarithmic function is the inverse of the function, right? So when we compose these two functions on each other out. So let's just see some of the properties, or at least the derivation of the properties, and then I'll state them in the slides so you can write them down, of what we'll look at today. So the first thing that we'll look at is base b of n in m. And like I said last time, I showed that this was equal to the log of n plus the log of m. So it turns a product into an addition. And that was one of the reasons why people were first interested in logarithms to begin with. But here, let's just go ahead and derive the formula again. So remember, b to the x is n, b to the y is m. So this is the same thing as the log base b of b to the x, because that's n, times b to the y. And then remember that when you multiply two exponents together with the same base, you just add the exponents. Those are the base b of b to the x plus y. And then, like I was saying, the way we defined our function was so that the log base b and the exponential function with base b were inverses of each other. And so this will undo that log base b, and we get an output of x plus y. But we have to remember what x and y are. One is the log base b of n, and the other is the log base b. Here we get log base b of n, that's x, plus the log base b of n. Okay, and the fact that this here is equal to this last line is what we'll call the product rule for logarithms. Okay, and again, I'm just sort of deriving, we went through this at the very end of class last time and sort of derived this. And there are three more rules that we'll have to be familiar with as well. And they're derived almost in identical. So let me go through and derive those, and then that'll be the last time we have to derive anything like that. And then we could just focus on action. Okay, but again, what I'm showing you here is why the rules are true. So, okay, and then we use this fact that you cancel a log and the next. So let's now think about what's called the quotient rule. In the quotient rule, instead of doing n times m, as you would do in the product rule, you instead do the quotient of the two of them. So in that case, we're going to look at what happens when you take the log of n divided by n. Now, the difference is that over here, instead of getting b to the x times b to the y, you would get b to the x divided by b to the y. Because again, n is b to the x, and m is b to the y. And then we would now use the fact that when you have these two exponents here, if you're dividing, you should get what power? So what should I put here in raised spot? It's not x plus y, but something different than x plus y. What should go based on this division by b to the y? Yeah, so in this case, when you divide by b to the y, you subtract off the y. So you'll get an x y up there. And again, the b and log base b will cancel each other out just like the last time. But instead of x plus y, you get x minus y here. And then here, when you replace the x with its log and the y with its logarithmic form, the only difference is you get a minus sign here. So what happens here is multiplication is turned into addition, but division is turned into subtraction. And the payoff here is that it's typically harder to divide something. Like the algorithm for dividing is much harder than the algorithm for subtracting something. So like if you were putting this in a calculator, this would be an easier calculation to do. Okay, but we'll exploit this in a little more detail. And again, I'm going to give you some time to write out the details of these rules. Product rule and the quotient rule, and then the last rule is related to exponents. So let's see how we would change this if we were looking at an exponent. So now, instead of looking at n times m or n divided by m, we'll look at n raised to a power of m and see how that changes things. Okay? So now we're going to raise to a power of m. I have to use as much information as we had before. So remember, n is b to the x, and what we'll get is b to the x, and then that has to be raised to the power of m. Right? And all we're doing now is using, I guess that red is a little bit hard to see, so let me put that in white. So we're doing n to the, and then here it's b to the x raised to the power of m. Okay? And again, all I'm doing is replacing the n with b to the x. Now what happens is we can write this as a single base, b, raised to 1 power. What power should I write here without any parentheses? Yeah, it should be, so anytime you raise a power to another power, you multiply the two bases. So Anna's here is correct. You want to multiply x and m. And I'm going to do it in a slightly sort of funky way. Instead of x times m, like everybody is saying, I'm going to write it as in this form, m times x. And just remember that it doesn't matter how you multiply things, but it'll make the formula look a little bit nicer. Okay, so it's going to look way different than what we had here. Now what's going to happen is the log base b and the exponential function with base b still cancel each other out. But instead of x plus y or x minus y, we get m times x here. And then now let's just convert this back to logarithmic form. Remember, x was log base b of n. So this whole thing is going to be m times the log base b of n. And so now this is the output for the power rule. And what you can think about it, you can think about it here, and it moves it out to the front of the logarithm. Okay, so you can take exponents and move it out to the front. In other words, it turns exponentiation powers into multiplication, right? So it simplifies that as well. Anyway, that's the derivation for the main three properties that we're going to actually use to talk about the affinity on the final exam and other places. And again, this is just the derivation, so I'm not going to ask you to do anything quite like this on a homework. Okay, so what are our learning objectives? Well, there are a few. We're going to learn how to use the product rule, the quotient rule, and the power rule. And those rules refer to the three things that we just looked at right now, right? So is when we look at m, the quotient is when we look at division, the power rule is the one that we just derived here that gave us this m out in the front. Two main types of exercises that go along with these properties when you're first learning how to do them. It's expanding and condensing logarithmic expression. So we're not even going to have equations yet, because an equation has an equal sign in it, and an expression doesn't necessarily have an equal sign in it. And we're just going to sort of be rewriting them using these properties. And then we'll do something that we probably should have done last time. This should have been in the previous section, because that was required for the homework assignment. But we'll derive the change of base formula. We won't do any examples, because we've already seen examples on the homework that use the change of base formula. But we'll sort of show how the quotient and power rule and those sort of things lead to the change of base formula. And it's going to be really important that you know the change of base formula, because most calculators don't have like a base B logarithmic function button. So you'll have to use the change of base formula to compute the log 2 or some strange base. Okay, so we've basically derived the three rules, and what I'm going to do now is just sort of put them up on the slides one by one, and I'm going to give you guys some time to put them into your notes. And as soon as you're done with the slide, just give me a thumbs up. Piece written down. You'll have to commit these to memory. They won't be given to you on the final exam, but you will be expected to be able to use them. A lot of practice in 6 on Friday with using these to solve equations. Okay, so here's the first one. If you take the log of a product, m times n, then it turns into the log of the sum, right? So a product turns into the sum of the two logs of each of the factors. And again, like, I'm just going to give you guys a few moments. As soon as you've written this down, give me a thumbs up and we'll move on. And again, this works for any base whatsoever. So natural logarithms, base 10 logarithms, and any other base that you would like. Okay, so it looks like at least half of you guys have said you've had enough here with this one, so let's move on to the next one. The next one is, again, the quotient rule. The previous one was the product. The quotient means division. So in this case, you're doing m divided by n. And what happens is it turns into subtraction. So it's the log of m minus the log of n. So division turns to subtraction. Multiplication turns into addition. And as you're writing this out, I want you to notice something about all of these formulas. On the right-hand side, you'll see two logarithms, and on the left-hand side, you'll see a single. So when I was talking about that learning objective of expanding or condensing a log expression, that's sort of what's meant here, right? So if we're condensing a logarithmic expression, we're reducing the number of logarithms that we would see in the formula. So we'd go from the subtraction side to the division side. And if we were expanding a logarithmic expression, we would try to write out as many logarithms as we possibly could. And so we would go from the left-hand side to the right-hand side. But you should sort of see it as sort of expanding the number of logarithms or condensing the number of logarithms. And each one of these equations has those properties. Okay, and again, I'll give you guys enough time to give me a thumbs up, and once you have it in, let me know, and we'll go on and to the last property, and then finally some examples. Okay, and then here is the final one. It's the exponential one. I'm not sure why they switch it over to a lowercase n here, but it doesn't have to be a lowercase n. And again, the idea is that if you take m to the, you can always pull that exponent right down to the front of a logarithm. Okay, and this is going to be incredibly helpful. This is where the change of base formula is actually coming from. So. Okay, and then as soon as you guys have had enough time to write it out, we'll go from there. Again, the derivation or the reason why each of these statements is true is basically what we were doing at the start of class, and it comes from that definition of a logarithm, and really that's taking it to be the inverse of an exponential. So all of this is just coming from the fact that we took a logarithm to be the inverse function of an exponential. Okay, so it looks like everybody's ready to move on to some questions. So some of this stuff sort of in action. And again, what we're going to focus on now is using these properties to expand or contract our logarithmic expressions. And we need to get really good with sort of doing this so that in the next section we can solve some equations. So to solve a logarithmic equation, you'll have to be very well versed in this expanding and contracting of a logarithmic expression. So with one of them, and we'll look at this expression here. So we want to expand out this log base 3 of this rational function. Okay. And the first thing that you should do with something like this, if you're confronted with it in an affinity or an exam, is to simplify things as much as you possibly can first, okay? Before you do anything with logarithms. And here, there's a common factor in the numerator and the denominator that can be canceled out. So what can we factor out of that 7x squared plus 21x in order to cancel out some of these terms here? Yeah, so the first thing that we should do is factor out that 7x, right? And if we didn't quite see that 7x getting factored out, at some point we would have seen it sort of happen in something out that after we're done with the whole problem. But here we're going to have to sort of recognize that you can factor a 7x out of the top. So before you do anything, you should try to simplify things as much as possible, okay? So let's do that here. Again, this is going to be, I'm going to write this on the board and then I'll share the whole screen with you. Log base 3 of 7x squared plus 21x, all divided by 7x, and then factors down there in the denominator, x minus 1 and x minus 2. Okay, and let me share my entire screen. Again, we'll factor the 7x out of the top first, and we'll just leave the logarithm alone. So here we have a 7x on the top, and we'll be left with an x3 on the top, and then a 7x, x minus 2. And here we can cancel the 7x right away. And we end up with x plus 3 over x minus 1 times x minus 2. Okay, and again, the instruction here is to expand the logarithmic expression. It's not an equation, so we're not solving for anything. We're just trying to expand it, and what they mean by expand is write it out with as many logarithmic terms as you can. So the first thing that we can do is expand the division, okay? And we'll turn this division fraction. So this will be a log base 3 of x plus 3 because that's what's on the numerator, and then minus everything in the denominator. So log base 3 of x minus 1 times x minus 2. Okay, so we use the quotient rule at this point. And if you're looking to get partial credit on a final exam, you should show every single step, right? For some of you, it may be possible to just jump right to whatever the answer is that way. So if you include more steps and you're showing each part of the rule that you're using at each point, then there's a lot more room for partial credit. So make sure that you're showing your supporting work as you're doing problems like this. Okay, so now we have two logarithms, so we've expanded the division, and then we can expand this multiplication and now rewrite it in a format that has 3 logarithms. Okay, so this is going to be log base 3 of x plus 3, and then parentheses, because this minus sign is on the outside. Here is 1 plus base 3, so log base 3 plus log base 3 of x minus 2. Okay, so now let me distribute this negative sign. I mean, this would be fine right here. This would be completely expanded. We can't expand any more logarithms out. There's 3 logarithms here. But let me go ahead and distribute this negative sign and point something out to you that maybe you're noticing. This is log x plus 3 minus log x minus 1 of x minus 2. And again, that's all base 3. I'm sorry, and I was distributing the negative sign, so this one should have been minus. Okay, so the point that I'm making here is you'll notice that we've the stuff that's in the denominator, and we're adding on the stuff in the numerator. So even if we didn't see that this 7x canceled out, if we had factored everything, we would have got a 7x over here plus 7x, and then a minus log of 7x over there, and they would have just sort of subtracted. Okay, so one part here is just to say the stuff in the numerator is the stuff you're adding, the stuff in the denominator is the stuff you're subtracting off. Okay, and this would be the expanded form of this logarithmic expression. And we'll also be interested in going in reverse, right? So somebody might give you an expression like and say condense that expression. What they mean by condensing the expression is to reduce the number of log base 3s that you see in the expression. And you'd have to go all the way back up to this, where there's just 1. Okay, I guess it would be here, 7x on the top and bottom if you're going in reverse. Okay, so that is a typical question where you're working with expanding a logarithm. And notice really the base played almost no factor. I had to keep track of it as we're moving around. So when you're using these properties, really what base that is being used doesn't really matter too much. When we're starting to solve some of the bigger role. Okay, so here's another one. Let me give you guys a moment to try and do this one on your own. And once you have the answer, type it in the chat because it's actually pretty simple answer. Okay. And it's kind of funny because I said means write as many logarithms as you can, but in this case we'll that basically the same number of logarithms. So saying expand is sort of a funny, it doesn't always mean there's going to be more logarithms. So once you guys have it, put it in the chat. And here we'll have to use the power rule as well, right? So that's exactly right. We want to do the quotient rule first with the subtraction, but then we'll also need to pull that x squared down the square down into the front using that quotient rule. I'm sorry, using the power rule. Okay. Yeah, so the idea here is you get this natural log of 1 minus the natural log of x squared. That's your first step. And then your second step is to then use the power rule to pull the 2 down into the front. So this is natural log of 1 is 2 of x. And I should say, before I was saying, expand and write as many logarithms as you can. And it looks like there's 2 logarithms here, but there's not. There's really only 1. Why is the natural log of 1? This is something that will help you out on the exam. This is when you type natural log of 1 into your calculator. This is your answer. This guy right here. ln of 1. What do I have to raise e to in order to get that? And by the way, it's the same for any base. The log base b of 1 is always the exact same thing. It's always 0. And that's again because b 0 is equal to 1. So this is really 0. So this is 0 minus 2 times the natural log of x. And if we simplify, here's the expanded form. Okay, the expanded form in this case is -2 times the natural log of x. And you'll notice it just has the same number. Let me write the original expression here. It has the exact same number of logarithms as the original. So expanding, I guess to be a bit more clear about exactly what we mean by expanding, let me just go back to the rules really and point out what's happening here. So expanding means that you're going from the left side of these rules to the right-hand side of the rule. Okay? From the left-hand side of the rule to the right-hand side of the rule, from the left-hand side of the rule to the right-hand side of the rule. And in most instances, you get an extra logarithm, but not every instance. For example, here. And sometimes that extra logarithm can disappear, right? Especially if it's the natural log of 1. Now, there's another way to do this as well if you sort of mess with the exponents first. So let me show you that method as well. You could have also written this as the natural log to the -2. Because 1 over x squared is the same thing as the -2. And the power rule in one step and get right down to this. -2 times the natural log of x, bringing that -2 out to the front. Either way would be correct, but the really nice thing about this one is that you should be careful about the word expand here. What they mean is just apply as many of those properties as you can. Okay, so that's another good example. And I'll just give everybody a moment to, if they would like, ask and copy this down. And if you're ready to move on, just give me a thumbs up. We're moving a little bit faster than normal. I'll give you as much time as you need. And again, this is a really good one to know. Anything to the log of 1 is going to be 0. Okay, so it looks like most people this one. Let's now check this guy out. We're going to want to give everybody a few moments again because we're sort of ahead of ourselves to work this one out on your own. And then, because it's just log base 10, it should be pretty easy to type into the chat. So as soon as you have it typed in and the correct answer is there, we'll go through and talk about why it's correct. And if you have the wrong answer, we can also talk about why it's wrong. I just want to give everybody a chance to think about the question. chance to get it right. So as soon as you get it, post it in the chat, and we'll move from there. Okay, great. So Anna has the right answer here. And I'll give everybody else a few moments maybe to think, and then we'll talk about why this is the correct answer. Okay, so let's go through this one. And really, again, the idea here is to take division to subtraction, exponents to multiplication, and multiply to, so we're going to look at this guy, which is log base 10 squared y cubed, all divided by z to the fourth. And like I said, you may be able to just look at this and write down the answer, but I would really try to avoid doing that because it's easy to make a mistake that way. And if you show me all of the steps in between, like we're going to do here, then on an exam, if you do make a mistake somewhere, then we can give you some partial credit, right? So you can show me that you know the properties of logarithm. Okay, so the first thing we'll take care of is the division, right? So that turns into subtraction. So that becomes log base 10 of x squared and log of z to the power of 4. The next thing we'll take care of is the product. So we'll split this up. And this becomes the log of x squared plus the log of y cubed minus the log of z to the 4th. Okay, so we've now used the product rule and the quotient rule. And then finally, we'll apply the power rule 3 times. We'll bring this 2 to the front. We'll bring this 3 down to the front. And then we'll bring this 4 down to the front as well. And we end up with 2 log base 10 of x, log base 10 of y, minus 4 log base 10 of z. And this is the expanded form of this logarithmic expression. Not trying to solve, not trying to solve a problem. We're just trying with as many logarithms as we can, applying those properties as many times as we can. And the purpose of these exercises is really to give you, a starting point for using these properties, right? We're going to use them to solve some equations on Friday, but this is just getting you sort of used to how these properties. Okay. So here's one, and let's do one now where we're sort of going in reverse. So here, we're going to rewrite this one completely as something like the log base 3 of something, okay? So the first step is, let's figure out what that something is, right? So when you get a chance, tell me what you get inside of those parentheses, and then we'll talk about the details from there. So we want to combine them together and write them as a single logarithm. And again, the question here is, what's going to go inside of the parentheses when we write it as a single logarithm? All right, so let's hear it. What do we get here, guys? How do we get this thing inside? Yeah, it's going to be 20, right? How do we know? Well, it's going to be log base 3 of 5 times 8 first minus the log base 3 of 2. That's just using the product rule. And 5 times 8 is 40, so you could have written it as 40, but I'm just going to leave it as 5 times 8. And then subtraction means you divide by 2. So this is the log base 3 of 5 times 8 divided by 2. And 5 times 8 is 40. 40 divided by 2 is 20. So here, to write it as a single logarithm, 3 of 20. Okay. Here's a slightly harder one. Here, the 0.5, you should think about it as 1/2, and you can rewrite it as a square root when you bring in the exponent. So again, we're going in reverse now, and we're going from expanding instead of expanding, now condensing or contracting. And your first step here is to take into account the 0.5. So before you apply any of the other product rule or the quotient rule, you should bring in that 0.5. And then you should also pull in the 3, and I'm running out of space here, so let me rewrite what I was going to write. So you should also take this 3 and bring the 3 up into the exponent as well. Okay. So here we should get that log base 10 of 5 plus log base 10 of 3 to the 0.5, x to the 0.5. And then minus log of 7x minus 1. We're going to bring it and write that as the log of plus 1 all raised to the power of, x minus 1 all raised to the power of 3. Okay, and what I was saying before is that this x to the 0.5 is really the same thing as x to the 1/2, and x to the 1/2 is really the square root of x. Okay. And then now, combine these comes the log of 5 square root of x minus the log of 7x minus 1 plus the log of x minus 1 cubed. And then from here we can combine this one and this one together. I'll leave the subtraction last. And so those two together become the log of 5 times the square root of x minus 1 to the power of 3, and then minus the log of 7x minus 1. And then now our final step here is to just subtract this guy, and when we subtract, that brings it in. And so writing this as a single logarithm gives us 5 times x minus 1 cubed divided by 7x minus 1. And this would be the condensed version written as a single logarithm. Okay, so that 3 turned into a power of 3, and it showed up in the numerator. 5 turned into a square root of x, and it showed up in the numerator. And this 5, here, as it was being added on, just turns into something in the numerator. We were subtracting the 7x minus 1, so that appears as the factor down in the denominator. So I think we have two more examples, and I'll go through these ones a little bit more quickly just because I think we're sort of getting the hang of what's going on here. Here, it's tempting to bring the 4 in all at once, but I'll wait to take it as it's 4. Instead, what you should do is bring the 3 in. And let's go ahead and skip a couple of steps so you can see sort of maybe how to do this by skipping steps. Now, again, I don't recommend necessarily doing that on an exam because you won't get as much partial credit if you get an incorrect answer. But if you're confident enough, you certainly can move through these a little bit faster. So here you would get a 4 on the outside. That 3 would be brought in as log x to the power of 3. And then we're plus the log of x plus 5, so that would be like multiplying by an x plus 5. So you'll notice I use both the product rule and the power rule. And then I'm subtracting a 2x plus 3, so that'll turn into a quotient divided by 2x plus 3. So that's combining those 3 terms without taking the 4 into account. And then now the 4 is just on the outside of the logarithm, so I can bring it in as an exponent. The log of x cubed times x plus 5 over 2x plus 3, and then all of it is raised to the power of 4. Okay, and so we've condensed this down into a single logarithm, and here by condensing the logarithm. And again, you'll have a lot of practice in Infinity. I think there's probably about 20 questions here that ask you to do the same sort of thing. Okay, and then just to give you a sense, let me go ahead and do a question that appears in the Infinity homework. A little more affection, but it'll give you a sense of why we're interested in using properties and condensing something down. So here we're given a logarithmic expression on the left-hand side, and it's equal to the log of a. And we would like to solve for a. And the way that you'll solve for a in an equation like this is to first condense the left-hand side. So you want to write the left-hand side as a single logarithm, and then once you have both sides of the equation, you can get rid of them. Okay, so here on the left-hand side, you're going to get a log. There's going to be an x because you have that log of x, and then you're going to have y to the 1/3, but it's going to come down here, being subtracted. And then there's the power of 5, and it'll be up in the numerator because you're adding it up. And this whole thing should still be equal to the log of a. Okay? So here I'm just sort of applying this property at addition signs. This was the 5 out in the front becoming the exponent. This one had subtraction denominator in the bottom of the fraction, and the number in front was 1/3, right? So again, here we're using the product, quotient, and power rule. But we're not quite done. Here, it's asking us to solve for a, and you can solve for a by remembering that the inverse of the log base 10 is the exponent, exponential function with base 10. So here on this side, we could take 10 to this power, and it would be equal to 10 to this power, and that'll cancel the log out on this side, and this, and times z to the 5 over y to the 1/3 is equal to a. And so this is what the solution would look like here for this equation. Now, this one's done here completely in terms of variables, but in a lot of cases, you'll get something like a is equal to a number or something like that. And we'll get more into those in the next section. But you'll notice that we've completely removed the logarithms altogether from the equation. And that will be pretty prototypical of what happens for logarithmic equations. Okay, so one last thing, and then I guess we'll sort of finish class a few minutes early. The change of base formulas. And like I said, we've already seen these, and they're the method that you'll use to actually compute a different base logarithm on your calculator. So if on the exam you're asked to compute the log base 1/2, for example, of a number m, compute the natural log of m, and then divide it by the natural log of 1/2, or whatever the base was here. And your calculator will have a natural log button, an L button, and so use the natural log button to compute any base logarithm. And the same thing is true for the common log as well. If you wanted to compute the log base, you could just do the common log of m divided by the common log of b. And remember, the common log is just the log base 10. Now, I'm only writing it down for these two bases, the natural log and the common log, but the formula is true for any log at all. And instead of doing some examples of this, I think there are like 2 questions at the end of the homework assignment. I'm just going to derive it for you, and then we'll sort of end class there. So again, the formula here, let me just put it back on the board, is this guy. And I'm going to put some stuff up on the board, and I'm going to leave this up for the moment in case there's somebody still maybe writing down the details. Okay, I said I was going to write some stuff down, but I'm not. Let's just start off by looking at the log base b of m. And let's say we typed in the calculator and we got out something like x. Okay, now what I'm going to do is rewrite this so that it's in exponential form. And exponential b to the x is equal to m. And now I'll take the natural log of both sides of this expression, because if b to the x is the same thing as m, well, the nat x is because the natural log of m. So again, I just wrote down this, you typed in, you're interested in this number, it comes out as x, put it in this form and take the natural log of both sides. Now this x we can move out to the front. This becomes m natural log of b is equal to the natural log of m. And then finally we can solve for x, right? And solving for x gives us the natural log of m divided by the natural log of b. Okay, and if we plug all of this back into the original equation up here, we get that this natural log of m base is the same thing as the natural log of m over the natural log of b. And the log base 10 instead of the natural log here, and we'd still end up with a similar sort of formula. And in both cases, what you get is this guy here. And this is why your calculator doesn't have an arbitrary base logarithm button. Instead, it expects you to comply the log of b. And again, I'm not going to do any examples of this. We've already seen it in the previous homework example. But certainly be aware of it, and remember, this is how you'll compute logarithms numerically on an exam. Okay, guys, have a nice day, and on Friday we'll finish up 6.6 and 6.7, and those will be the last 2 chapters of the semester. Then we'll start reviewing.